friend, Daniel Terno, Professor Daniel Terno from Kerr University in Australia, to talk to us about black holes and radiation and semiclassical gravity. And Daniel was born and raised in South Korea, part of the USSR. He completed undergraduate studies at the technical in Israel with Harris and his PhD in 2003. From 2003 to 2006, he was a postdoc at the United on gravity. That's pretty much where the knowledge. Then joined the faculty of Kerr University in Sydney in 2007 and is now a professor in the School of Physical Sciences. He has worked on foundations, and optical tests of gravity, and most recently, his research has focused on semiclassical black holes and related topics. Outside physics, Dan enjoys sport and reading, gym, kickboxing, and diving. Medieval and far eastern history along the I really love to talk to them because I can learn lots of historical stuff from him. So let's talk.
Thank you for the introduction. First of all, thank you for the invitation. It's great finally to be in Shanghai for more than 4 hours between the flights. So far, I'm enjoying it very much. I hope that you will like my story. I tried to follow the instructions and the brief I was given. We'll see whom to blame if it doesn't work. So yes, first of all, my topic will be indeed black holes, Hawking radiation, a little bit of information, but mostly it's about the question, what it really takes to have a black hole. Now, before that, I have to thank organizations that fund me, and also I'm a little bit on an advertising mission, in particular, advertising of a joint PhD program with MacQuarie that signed an agreement with your university, actually. And Fudan is one of MacQuarie's preferred partners. To tell the truth is because to very large extent, MacQuarie tries to get into the big league instead of perpetually being just at its boundary and team up with great partners worldwide. Fudan is one of those partners since, I think, last year. Conditions are pretty good, so talk to your supervisor first of all. If it will, if you, well, I don't know what you have to do here, but at Macquarie, there are allocated scholarships which are pretty decent, with conditions, I would say, slightly better than for normal international students. So, but here they are. And you can spend between a year and 2 years in Sydney, and it's really a lovely place. At our department, which has a lot of good physicists and interesting people, which is also located in quite spectacular place. The main drawback, if you are into surfing, it's still about 50 minutes from good beaches, so it's not on the seashore, no matter what is implied in some advertising. So that's essentially the story. That's actually it's a law building. It's like, it's Parkinson. No, it's Parkinson. No, actually, Sciences building now is actually constructed. It's pretty
spectacular law buildings too.
Yeah, it's it's just by the illustration of Parkinson's law. Once something is going to be removed by AI, you get the most spectacular building. Again, that's sort of now that was the promo. Now let's get to the physics. And as a teaser, I'm showing, now where is the pointer actually? Now, I managed to kill it. Yeah, not very smart. Now, if I press this, no, here it is. Oh, here it is. Yeah, see, a theory, so theoretical this is what happens when you work on theoretical optics. So the motivation, I'm going to show a little bit of information loss problem, but this is not about it. Motivation, because for me, I'm trained in quantum information. I ran almost by accident. I learned about information loss problem. It became very interesting. A bit later, I learned that the mode of description of pure states going into mixed states, which is perfectly normal in quantum information. It's just, completely positive operation. What is so curious about it? The main equation was proposed in the same 1976 when Hawking somewhat apologetically introduced his superscattering operator, and it just showed how much two communities were not talking to each other. So the traditional formulation of the information problem is here. Description, pure state goes to a mixed state, and well, in reformulation of Bob Wall, if those correlations are not restored, the information will have been lost. A lot of arguments about it in the last 50 years. From the point of view of psychoanalysis, I think it covers all possible resolutions, from trying to exercise the problem, to deny that it exists, to accept it as a feature, to resolve it in very many ways. So after teasing it out, let's see. What I'm going to talk about, I'll look at those paradoxes. Now, not by training, but by, say, heritage from Einstein, Rosen, Perez chain of descent, I do play with quantum foundations, and I will look at the information loss problem just as a normal quantum paradox. Not how to solve it, but what are the components, what are the ingredients, what do you need to claim that you have a paradox, and we'll analyze the physical part of this paradox. Once we know what we really need from a black hole to have been able to formulate the paradox, we forget about it. We just look at these physical elements and see what those elements, if true, can teach us about black hole physics. Then we'll move to implementation and consequences, particularly in spherical symmetry, where it's relatively easy to work out. A side trip, sci-fi, and physics. We'll talk about wormholes, which are very close to physical black holes. And if we have time, we'll talk also about observations. Now, from the point of making the paradox, like what do we have in, actually, how do we have paradox, like EPR paradox or anything else in quantum foundations? What we really have, we have a set of classical ideas. We have classical elements in the theory. We also have classical expectations, things that we believe the system, the theory should give you. Then we remember that actually, oh yeah, there is quantum mechanics. It comes with constraints and requirements and specific quantum features. And we somehow want to have it both. So we need to combine it and try to obtain probability distributions, which both satisfy the rules of quantum mechanics and conform to our classical expectations. And that's what leads to a paradox. Sometimes the thing may be even internally inconsistent, as analysis of wave-particle duality honestly really shows, or we get a consistent theory which is not confirmed by experiment. And that's about celebrated Bell theorem and all the related results. What's important, that the same pattern persists also if we look at information loss problem. We have classical concepts, and the main classical concept is existence of the event horizon. And of course, we have quantum elements, and this is Hawking radiation. Now, why I number them 1 and 4, you will see at the moment. Now, here is a bit of historic description I picked it up from a review of Hayward, and that's essentially evolution of the views of Stephen Hawking on the event horizon, starting from very early on and ending in his later works. So from event horizon, which is essential object in defining the black hole, to event horizon that maybe never have been really formed. It also rhymes with different views of the problem. So, for example, there were two reviews published back to back in 2017. One by Don Maroff that resolved the paradox by one of the slate of hands. Another one by Bill Andrew and Rob Wald, which said, yeah, information is lost, so what? And if we're looking for more modern reviews, yes, but it took time. It took time to realize. But also the point is that to have a paradox, you need the event horizon, because you need, let's see what we need. Let's be more careful. We need a bit more. We need a scattering scenario. We need finite time of formation of the horizon that we use to trace out the system. Because we have to have before when we have information, and we have to have after. And this before and after, not from the point of view of some, brave Alice that plunges into black hole. It's from the point of view of stay home, distant observer Bob. We really need in and out settings. We do need, not for the black hole physics purposes, but for conceptual formulation of the paradox, we need the event horizon. Because loss of information is fundamental and not just related to our inability to do experiments or, not insufficient budgets and stuff like that, is not when we trace out because we don't know. It's only if we trace out if it's in principle unknowable. And for this, we need something absolute that separates what we have, what is accessible from what is inaccessible. We really, to formulate the paradox, we need the event horizon forming in finite time of a distant observer. Now, the language that we use is semi-classical language. What firewall people said in a pictorial language, there is no drama at the horizon. We still can use semi-classical concepts. In more technical terms, we believe that standard semi-classical physics applies most of the time for most of the space-time. And particularly, its implementation of weak cosmological censorship, that if there is a singularity, it's hidden beyond the horizon. That's, like, again, a technical assumption that we need to formulate the information loss problem. There are restrictions on there are different types of singularities by how strong they are. I'm going to use the weakest possible definition of singularity, and we will see that there are additional ones. So basically, I'm going to stick just to scalar curvature, curvature scalars obtained from Riemann without any additional derivatives, for example. So basically, it's second order in derivatives of metric. There are more varieties, and all of them assume this and something else. I'm trying to be, as accommodating to the position as possible. And yes, we need nearly thermal Hawking radiation. Its purpose in life to generate high entropy reduced state. Now, again, it's a very interesting question about how we define the state, what we do with it. Not my purpose today. I really want to see what are the classical bits that we need. Now, let's change attack a little bit. Theoretically, as you probably know, idea of something which later became known as a black hole goes very long time ago to late 18th century. By the way, this is not the abstract. This is the title of the paper. Letter by Reverend John Mitchell on stellar properties and observations, read in 1783. And somewhere deep down under in this paper, in section 16, there is analysis of very massive bodies. And particularly, it found that if it's sufficiently massive and dense, all light emitted from such a body would be made to return towards it by its own proper gravity. Now, it's proper gravity, of course, is not what we call proper gravity now, but yes, maybe as all those Newtonian results up to factor of 2, and here I think there was no factor of 2, size of a black hole was found. An interesting feature, that's a review or opinion piece from Nature Astronomy from 2019. If you ask people who work with black holes, starting from mathematical relativists, theoretical physics, quantum gravity, blue quantum gravity, string astronomy, galactic astronomy, and you ask them, okay, so what is a black hole? And then you try to map the answers and see what's common in them. My impression that the only common thing in those answers is that black holes is the thing that I happen to work on. So there is no uniform view of what is a black hole. So when people discuss again information loss problem, and when they even don't agree on what is the black hole, we get to rather old, well-known classical situation that if names are correct, we have problems with the meaning, and with problems in the meaning, we have problems with the business. Oh, wow. Indeed. Yeah. Well, my Greek is also not perfect. It should be different marks. Now, the picture is taken actually from Athens, from Agora below the Acropolis. So let's see what. I know there is a variety of different definitions. We're not going to deal with them. I'd like to focus on two using terminology of Valery Frolov: mathematical black holes and physical black holes. So mathematical black holes is just a standard thing that we got in textbooks, and the most formal part is everything which is inaccessible to the future null infinity. So anything which is outside the past of the future null infinity, bounded by the event horizon, that's a black hole or black holes. For this, to know it, we need to know the entire evolution of the space-time. It's global entity, it's teleological entity, it's not locally distinguishable. Valery Frolov proposed physical black holes, which are essentially trapped regions of space-time. Roughly, because there are a lot of definitions of how we define them and how we define the boundaries, less important in spherical symmetry, regions where both ingoing and outgoing null geodesics have negative expansion, are trapped. Boundary of this region, where the outgoing geodesics have zero expansion, its marginal outer trapped surface. Its evolution is the apparent horizon. This is what we take as a physical black hole. Now, this definition is local. It might be observer dependent. It doesn't assume anything about the event horizon. It's about trapping here and now, no promises and no guarantees about the future. So that's almost what we need. The difference between them is very stark. So here, for example, event horizon bounds the black hole. Boundary of the locally trapped region is inside the event horizon. And this is a generic feature. In classical general relativity, if a null energy condition is satisfied, the apparent horizon is inside of the event horizon. This is a rather old and well-known theorem by, well-known in narrow circles theorem by Hawking and Ellis. What we also know is that if we do have Hawking radiation, so this is a schematic and probably physically inconsistent picture of black hole formation and evaporation, just the space-time structure. The apparent horizon goes outside the event horizon. And of course, we know that null energy condition in this case is valid. Cool. So let's define the rules of the game. We're not going to play with paradoxes. We just will look at the consequences of the two essential ingredients of this paradox. The framework in which I'm going to work is a classical, well, we assume classical structure of the space-time. So we still use the metric to describe the space-time, classical concepts like trajectories, horizons, they are all valid. Dynamics, we give it as a semi-classical or effective. I'm going to focus more on the left-hand side, on the Einstein tensor. On the right-hand side, we have a renormalized expectation value of the energy momentum tensor. We might have cosmological constant in it. We might have any actually metric theory of gravity, so all the higher order terms go here. Counter terms, if it's effective theory, then results of integration of high frequency degrees of freedom. Let's look, so we'll look at geometry. And we still assume that collapsing matter is described by motion in this self-consistent metric. So on the right-hand side, we look at the entire energy momentum tensor, not splitting them into unperturbed collapsing stuff and whatever happens later. What we do not assume, we're going to go local. We do not assume global structure. We do not assume if there is or there is no singularity. We don't assume type of the quantum state, so that both strength and weakness. We don't assume Hawking radiation. We just assume that there is a black hole. And by this, and elaborating on two grades about the names, we take a physical black hole as a light trapping region, which forms in finite time of a distant observer. That's a very important, turns out to be very important assumption. I'm still considering isolated black hole. In principle, there is nothing wrong with any black holes, with any number of black holes, and there is also no. I really don't need it. And there is, for example, we'll see. Yeah, I'm going to show it. It very almost trivially embeds into in the analysis or in some other cosmology. And the metric can be matched to the metric outside, metric distant from the horizon of any form. And we can use it for analysis of binaries or
you consider a kind of isolated region of the entire universe.
Yes.
And which may have a junction condition to connect with the rest of the
universe. Yes. And I'm trying focusing only on the features which pertain to the local trapping of light in whatever form it embeds into a bigger picture. So what we require that for a distant observer, it happens in finite time, that there are no curvature singularities. So that's a requirement that there is no singularity up to the horizon if we're going from the outside, and we don't require it in a strong form. If you look at the classification of singularities, absence of scalar curvature singularities is one of the lowest on the rung of severity of the requirements. As an afterthought, especially after playing with wormholes, I'm adding another not very heavy condition. Remember, we're working semi-classically, so our theory should be consistent. And consistency means a violation of the null energy condition is fine. But we know that null energy condition violations are bounded by quantum energy inequalities. And we want to be consistent with quantum energy inequalities. So we don't want stuff to be too unreasonable, simply because if quantum field theory and curved background breaks down, our formalism is inapplicable. So with that, let's look at what we actually have observationally. We have more than 100 dark, massive, compact objects. There is a whole bunch and almost contact sport of the theories that describe them. Since 2019, we know that there are objects, there's objects with light rains. Now, in this zoo, in spherical, this is what happens when So that was supposed to be Greek epsilon. We can introduce compactness, which tells us how the putative model or putative object, how close it is to a Schwarzschild black hole of the same mass. So the same mass, so we have Schwarzschild radius, twice the mass in Planck units. The objects are bigger. To have a light ring, we need this compactness to be smaller than 1/2. Now, the guys that go from 1/8 are usually labeled exotic compact objects. And that's because of the Buchdahl's theorem that was proven in 1959, started with reasonable conditions, including satisfaction of null energy condition.
Sorry, I didn't catch yours. Why?
That's a terminological problem. We wanted PBH, like for physical black holes, but PBH is taken. Everybody in black hole community assumes that PBH is primordial black hole. After a referee complained, but when for our review, for example, we asked, please tell us how we should pose it. So at the end, I decided to just go with Greek physics. So I will do 5 PBH. We tried PBH, and every time we had to ask people because if I in the same paper we had to abbreviate both physical and primordial. Then I started to use PBH, and that was considered to be demeaning to the community. So physical black holes are Greek. That's why Socrates. So yeah, so the point is that if you assume those reasonable assumptions, there is nothing which can be static between compactness 1/8 and the black hole. So to cook up models which are almost compact as black hole, you need to violate at least one of those assumptions. Now, let me give you a secret. What we call physical black holes, violate all of them. Anyhow, we have either physical black holes, trapped regions, maybe we have mathematical black holes, so we may have event horizon. Those black holes might be regular. That means maybe there is no singularity. And there are models of wormholes whose throat is the size of the Schwarzschild radius, so we also stick them here. Now, from the point of view of a distant observer, 3 things can happen. Again, classical picture. 1, indefinite collapse. So just horizon is formed asymptotically, like in classical collapse models. So that's the compactness goes to 0 at finite. People cook up models of ultra compact objects, exotic objects. So we have a transient or an asymptotic object where compactness reaches minimum at some time, maybe finite, maybe asymptotic. We are interested in this formation of a physical black hole, that means trapped region, with apparent horizon and infinite time of a distant observer. That's our goal. Now, few words again to justify assumption of the finite time. First of all, as you see, it doesn't have to be. There are 2 additional alternatives. You need it if you want to talk about information loss, because at least in spherical symmetry, it's rather straightforward to show, to be able to talk about event horizon in finite time of a distant observer, you need apparent horizon in finite time of a distant observer. That's one. Another one, those are typical models of regular black holes. So on the left, popular in the literature, and that's Ashtekar-Ravelli black hole bouncing into white hole. As you see, from the point of view of a distant observer, that happens in finite time. So let's see what are, and they usually don't give any consideration to the price which is involved in forming those objects in finite time. We want to see what is the price. Yeah, and finally, of course, the sci-fi. If you want to traverse, yeah, wonderful. My spelling skills probably only deteriorating with time. And yes, and of course, if you want wormholes, traversable wormholes, you need to form them in finite time as well. All right, so let's see what are the implications. So again, in the interest of time and also interest of propaganda, let me put the high-level slide of what we're doing, why we're doing, what we're getting, and then we'll go into the details and you can tell me. So what we're going to do is three things in spherical symmetry that's particularly useful. We're going to use bad coordinates. We use Schwarzschild coordinates for two reasons. First, because time of a distant observer is related to the coordinate Schwarzschild time. Second, because they diverge. They're bad coordinates. A lot of quantities diverge in Schwarzschild coordinates next to the horizon. And what we're doing, we're building invariants, which are scattered, which are finite, from diverging quantities. So we essentially even teach the field theory. We learn from the divergence because things cannot diverge arbitrarily. They have to cancel each other. We don't have any extra consequences between n by n. So from here, we can learn the ways the energy momentum component scales, and then we can bootstrap it into getting to know what are the allowed classes of metrics near the apart horizon. Once we've done it, then we will work with null coordinates because it's easier, things are regular if you choose the right type of null coordinate. But the initial steps are done in Schwarzschild because Schwarzschild is bad. And occasionally it's good for you. So what we learn, just again, set of slogans. If we have a black hole, physical black hole, you can fall into it in finite time of a distant observer, not infinite time. Maybe you cannot fall into it, that's also a possibility, but if you do, finite time. Much more interesting, spherical symmetry, that means zero angular momentum. We get pairs, black hole, white hole, as a solution. So important thing to note is that if we get a black hole, it can only shrink. If we have a white hole, it can only grow. That makes life rather interesting. In Schwarzschild, but not in, if you assume physical black hole and you get the metric, then you begin to play with this metric, and the conclusion is that the info will be finite. It's actually once you get the metric, you just do standard analysis, and you see it. If you try to collapse thin shell in certain models, you get finite time of collapse. But again, that's sort of by design. You have horizon formed in finite time. You need to have something. That something is that null energy condition is violated in the vicinity of the outer horizon. We can find surface gravity and find that most of the generalizations are not applicable, but Kadama generalization is amazing. Inner horizon, if it exists, it's time-like for null. From null models, it's always time-like. Null energy condition is satisfied near the inner horizon. So black hole is sort of a transition region. You start from violating, then somewhere in the middle you neutral, and then you exit if it's regular black hole. It's satisfied. And then byproduct, some regular models popular in the literature simply wrong. They're inconsistent with finite formation time. But also some of the proofs of instability of regular black holes are not applicable. So that's a mixed blessing. Now let's look at it in a more technical way. So that's our object, Einstein and semiclassical Einstein equation, where we're going to work with this mostly. Those are two of the main assumptions. In spherical symmetry, that's the metric in the most general form, function h, f, which is, I should have written it here instead of next slide. It's 1 minus twice mass over radius. H and f are function of time and radial coordinate. The radial coordinate is really areal radius. Those are two geodesic families. We can get the expansion. Schwarzschild radius is 0 of the function f. let's say, largest, which is not on the cosmological scale. We can also have cosmological horizons here. So that's what we try to avoid. As I said, we use bad coordinates. We require self-renormalization to get finite quantities. We look at two scalars, trace and the square of the right-hand side. So more properly, it should be G mu mu and G double contract. So we really look at the geometry, which we interpret in terms of energy momentum tensor. And another trick, and that's useful to not to look at them, but actually introduce those ugly, no, they're beautiful once you get used to them, those combinations of energy momentum components and the function h. This way I can remove it from consideration. We'll see it in a bit. So 3 effective components, one, and you see one mixed, one co and one contravariant, 2 of them absorb those functions. And that's because if I look at these 2 curvature scalars, using these effective components, I have very simple expressions. Now, this relates only to the TR block. There should be, of course, theta theta, but with a little bit of work, you can prove that if it diverges slower than those components. So we don't have to consider it straight away. We'll look only at those and then verify that our solution is finite. With these components, we can learn about the scaling. And to have the finite values, we can assume a lot of types of scaling, but only 2 are viable. One where all 3 components go to plus or minus constant. Another one where they go to 0 as function f when radius goes to the Schwarzschild radius. We had quite a general argument that recently my students found a hole in it and found that some of my arguments were circular, and my collaborators happily went along with it. So a recent update that closes all the loopholes is here. So what we gain as well is that Einstein equations look simple. So equations for the mass functions very useful for the analysis of for the series analysis. We assume that the mass function is Schwarzschild radius function of time plus expansion, and see, it's just twice the mass. So it's honest answer. We started when our first papers were done in dimensions, and there that is standard definition for 5 dimensions. But basically, it's twice the mass. I'm also lazy to write number 2 at the time. So normal Misner-Sharp mass is just this n, but if to make generalization for high dimensions easier, people absorb into the function. To me, it doesn't make any sense. We pick it up, we look at look how it's called, and it was called C, and sort of we are stuck. So what is possible is if you play back and forth between energy momentum scalars and Einstein equations. If you want real solutions of the Einstein equations for the case k equals 0, 2 of those effective components should be negative. The one which is related to time and to the flux can be positive or negative. Type of the solution depends on its sign. So for k equals 0, well, actually, by assuming it, we define the structure of the metric. we get metric at the class C, K equals 0. And if we look at Schwarzschild coordinates, it looks very different. We get a square root term. For dynamical black holes for K equal 1 class, we have even weirder form. Now, because we have 3 equations and only 2 functions, there is a relation between the parameters of the metric functions. I mean, there are more for higher order, but those are most important. Rate of change, so for black hole, it's minus, for white hole, it's plus. Schwarzschild radius related to other parameters. There are no static K equals 0 solutions. Idea metrics, when we analyze them, they K0. All known static not popular black hole metrics are K equal 1. All known to me, at least, dynamical regular black hole models are K equals 0. So if you analyze what is done in general, it falls into one of those 2 classes. Now, to understand what's going on, it's really better to work in more usable coordinates. We can go to retarded or advanced null coordinate, analog of Eddington-Finkelstein. And what we find that, for example, if we look at shrinking Schwarzschild radius using advanced coordinate, using advanced coordinate leads to everything being regular, and we have a black hole. You can just calculate the expansion and you see it. If we have growing Schwarzschild radius, it's a retarded coordinate where everything is regular, and those are white hole solutions. Now, the main type of the solutions, as I said, correspond to K equals 0. In any case, apparent horizon is time-like. So it's more like time-like membrane of Thorne, Price, and McDonald and de Moor than conventional event horizon, and also conventional apparent horizon. It doesn't have space-like elements. Now, one of the consequences, as I mentioned, is finite infall time. You can really see what happens, let's say, to null rays. Incoming null rays satisfy this relationship. And when we go to the apparent horizon, it just goes to the inverse of the evaporation rate. If it's finite, crossing time is finite. Now, for static absorber, energy density, pressure, flux diverge. For geodesic, for moving absorber, they are fine. If we want to look in VR coordinates, the metric takes the Bardeen form. So just regular expansions, no dramas. If we want, we will see that if we want the standard Hawking radiation and Page formula to apply, we need to have the first expansion coefficient in VR coordinates to be 0. In general, especially we can get coordinate transformation. But near the apparent horizon, we can go from VR to TR both ways. That's just long form, not longish formulas that I'm not going to bore with you, but that's known. And for linear evaporation law, we can even get coordinate transformation between TR and VR fully analytically. Now, as an important consequence, null energy condition is violated. Let me to remind you, there is a hierarchy of different conditions on the energy momentum tensor. The weakest of them is a null energy condition. If it's GR, it's really just geometry and energy momentum are related. What we are doing, honestly, is the GR part. What we discovered that if we want to have solutions of the Einstein equations to be real valued, we must pick up the signs that force violation of the null energy condition. If we try to keep positive signs, we get complex valued solutions. That's essentially the fork where Joe Moffat in recent works goes to complex values and complex metrics. If we want real metrics, we have to violate the null energy condition. So a nice byproduct, you probably all familiar with various idea metrics. If we can get 4 of them, we can write them in ingoing or in outgoing coordinates, and we can have growing or shrinking mass. Now, 2 of them violate null energy conditions, and 2 of them don't. If they don't, they cannot correspond to anything which forms in finite time. So we have shrinking black hole and growing white hole. Idea case, like general case. One of the predictions that results that made me believe that what we are doing is sensible is actual honest full 4-dimensional calculation of regularized energy momentum tensor done by Levy and Ori for scalar field on background of the Schwarzschild black hole. They obtained components of the energy momentum tensor. And please look at the placement of the indices. This is the same placement like in the effective components that I picked. Of course, function h is identically 0. And as we go to the Schwarzschild radius, that means when the tortoise coordinate goes to -infinity, the 3 energy momentum components go to the same limit. That's a real hallmark property of k equals 0 dynamical solution. Sure, at any time.
So I remember in the scenario you pass the effective E in the right-hand side of the
Yes.
equation. So that in this scenario you estimate the non-energy conditions of T to get the non-energy condition of
Either way around. In this, because I'm really working this up. So what if I can identify R and T via Einstein equations, then it's really energy condition. But you are right. It's honestly, it's a null geometry condition, because this is what this is what the quantities that I'm playing with, and I'm associating them with the right hand side. When this is just the right hand side of the equation, where everything is lumped together.
So the T here includes the
It includes everything. Yes.
Okay.
Yeah. Now, how black holes form will be quick, but basically we just use the same decomposition for near formation scenario, just at the minimum of the difference between the mass function and the areal radius. Then before the black hole is formed, we have the gap. A little bit of easy analysis shows that black holes form at k equal 1 solutions and immediately transformed in k equals 0. So if we try to plot, for example, how regular black hole should look like now, I don't know if this sun forms, but assuming that it's a regular black hole, oh, I'm going to together. So that is outer apparent horizon, and that is the inner apparent horizon. And unlike conventional models, they are defined invariantly. You can define it by the expansion, you can define it by the crossing, you can define bigger, smaller. When you have blobs, different definitions give you different sections. Because they both have to be time-like in our approach, if you assume finite formation time, then you invariantly define them in spherical symmetry. That's what is different from conventional models. You can cross them only once. No. I mean, but again, we don't assume it. We assume finite formation time. Everything else is derived.
What is that? Like yellow curve?
Oh, yellow curve is constant time surface.
Oh, okay.
So that's a space-like surface, constant distant observer time, touching the moment of formation. Again, finite time of moment of formation. The dotted line is ingoing null coordinate. The dashed line that outgoing null coordinate. Green line is just time-like trajectory of a distant observer, which again you see he gets information that the black hole formed in finite time, and if it's really transient regular object, also gets in finite time information that it's evaporated. Few bits about difference between us and the general approach. Surface gravity, very important quantity. In static scenarios, whether it's Schwarzschild or Kerr, you have several definitions. They all give the same thing. In Schwarzschild case, 1/4 mass. They are very important because this is the quantity which allows you to formulate laws of thermodynamics, black hole dynamics as laws of thermodynamics. This is the coefficient. This is Hawking temperature. So it's really important quantity, and people do generalizations of this quantity to dynamical scenarios. There are several. And in general, if you have a dynamic black hole, they will be different. But usually they assume or argue to be close to each other. But this closeness assumes that function h is finite. The function h, as we've seen, is divergent. So for what is known as peeling surface gravity, you get either 0 or infinity, depending how you define it. You can get to more definitions and you get more quantities. On the other hand, Kadama surface gravity, introduced actually by Haver, is perfectly nice and perfectly finite. The only issue is that if you want to get the static result, you need to assume that the first expansion coefficient is 0. Okay, I'm ready to pay that price. An argument, if you want the first law to be applied to the apparent horizon, again, you need the first expansion coefficient to be 0. If you accept, and now that's an interesting point, I never seen a proof that pages of operation law has the same form in all coordinate systems. Looks reasonable. People just say so. So if you assume that this is so, you can identify the two metric functions. And you get that all this fancy stuff happens in a very narrow range, and the hair of a black hole is really short. You can fit it, because we don't assume anything about asymptotic structure. You can fit this formalism into expanding universe. So for example, if it's asymptotically de Sitter, all you have to do is to separate the energy momentum part for cosmological constant and everything else. And only one equation changes. Again, the known results fit into this formalism. So now we have a regular black hole in a static patch described by Schwarzschild coordinate in the de Sitter universe, which is what is accessible to the observer here. Again, distant static, nearly static observer, surfaces of different constant distant time, whether Schwarzschild-like or universal. Cool, but before going to the end, let's do something nice and a bit of sci-fi. Wormholes. Now, I know it's a very politically charged question if I ask audience, are they Star Trek or Star Wars fans? So I'm not going to do it. You see, I'm a person who watched Spaceballs before Star Wars, so I couldn't take the movie seriously afterwards. But yeah, but motivation actually was sci-fi. The famous paper of Morris and Thorne of American Journal of Physics from 1988, basically, they designed a wormhole to help their buddy Carl Sagan to write a scientifically reasonable sci-fi novel. And there they formulated 9 rules of making traversable wormhole. Now let's just compare them with what we are doing. They want spherical symmetry and static. Okay, our results so far are spherical symmetry, but can also be dynamic, and that's an important bit. We don't even really need Einstein equations. Any metric theory of gravity will do. We don't need asymptotically flat regions. Of course, the key property, there is no horizon. We have variably small tidal forces, finite curvature scalars. We want finite reasonable travel time. We want sub-universe scale resources. That means finite formation time. I cannot say anything about perturbatively stable. Unfortunately, that's something that we haven't played with. Reasonable energy momentum tensor. Again, reasonable now is it's okay to violate the null energy condition. It's not okay to violate quantum energy inequalities. Two popular example is Alice, which was much earlier than Morris and Thorne black hole, wormhole, or more recent Simpson and Visser wormhole. Now, okay, as I promised sci-fi bit. Actually, that's the case. My kids talking to me after I published a paper on wormhole. And I was forgiven only after giving a quick explanation. Now, if we look at sci-fi, there are two ways wormholes exist in sci-fi. One, in most sci-fi, I think from Stephen Liu to anything, here they are formed at will with some resources, whether it's interstellar or whatever it's created, and you travel through it. Another one, sort of assumed in Eve, definitely in the Honor-Harrington universe. They were formed somewhere around Big Bang. They're naturally occurring. You just find them and control them. They're a precious resource. You cannot build them. So I was forgiven when I told that my disapproval of wormholes doesn't apply to this scenario. Okay, so more seriously, why we do want to play with wormholes? Because surprisingly, they becoming more respectable alternative formulation of a black hole model. For example, in paper of Cardozo, Franzen, and Pani from 2016, they analyzed a wormhole. We'll see it in a moment. That from the outside looks more and more as a Schwarzschild black hole, asymptotically for some value of parameters, it's exactly like Schwarzschild black hole. If you calculate its quasi-normal modes, they will be very different and it will be shown in potentially in long-term tails of the black hole ring down. So that's also a serious contender. Now, what do we do in our formalism? We have all this. The only difference is that H and F are now absorbed in explicit expressions into this form, and these together they should be finite. Doable? Not really. So what is the wormhole throat? It's marginal outer surface plus flare out condition. That particular additional. So basically, what I have to do, thanks to Hogberg and Visser, I find solutions F equals 0 and then check if they satisfy the additional condition. But all our approach is based on finding F equals 0 solutions and playing with them. So what we found that, first of all, popular models, they're static models, and they, surprise, surprise, all, no, popular models, continuous models, are all K equal 1 class. It's, again, you can analyze it, just a bit boring, but you find that the all K1 class solution. Now we know that there are no static K equals 0 solutions. So that was my original argument, that if you try to purpose-build dynamical K1 wormholes, you get burned and destroyed when you get infinite tidal forces, and you cannot get the limit from K equals 0. That was wrong. You can get the limit from K equals 0. Again, going to the limit, significance. So there are two ways of extending models that people cooked up as solutions for models of black holes. You can either really let it go indefinite from minus infinity to plus infinity, two-sided, or you can have like a dead end. In one case, the spectrum will go to the Schwarzschild limit. In another case, like here, it will not. And that's the models that are considered as contenders for black holes. So, right, we can have a limit of k equals 0 solution to those static wormholes. We just have to do it in a particular careful way. What comes on the way of living happily ever after are quantum energy inequalities. If we look again at the infalling Alice into a black hole, or our Alice that tries to escape a black hole, we get that energy density for infalling Alice is finite. Negative and finite. That's fine. What we would be getting is infinity, this divergence, going to infinity, so integrating, going to logarithmic divergence, if you can exit with positive radial velocity. But you cannot exit a black hole with positive radial velocity. You just analyze how it happens. What happens on exit is that you are just overtaken by the apparent horizon. So in black holes, this doesn't happen. In wormholes, traversable wormhole with finite velocity is part of the design. So by design, you have this, and that means while it's dynamic, you get violation of quantum energy. So dynamically, so long as semiclassical physics, now continue. Dynamically, so long as semiclassical physics is true. Okay. We get divergences, and that means quantum field theory of Kerr breaks down. Our entire approach is inconsistent. So if we have traversable, if we can build traversable wormholes, that means we are breaking semiclassical physics on large scale. If you believe in semiclassical physics on large scale, wormholes cannot be created apart from early universe quantum gravity regime. And to finish, without going into too many things, just one application. About 2 years ago, there was a very popular controversy. It's question, do black holes couple to large cosmological structure? So the group of Kerr developed some formalism and also analyzed a lot of data about galactic black holes. And the question that they investigated was this. So if a black hole was created at certain redshift, okay, certain radius of the universe, and now we're observing this black hole at current epoch, let's parameterize the law that relates black holes then to black holes now as a ratio, as a product of the initial mass, ratio of the current to the then radius of the universe to some power. So if power is 0, there is no relation. Power may be negative, power may be positive. They got that the most probable result is coupling its power equals to 3. That means black holes also can be candidates for dark energy. Now, there was an immediately rebuttal. I'm not competent in observational cosmology and astrophysics, so I cannot say anything whether it's valid or not. One thing that we can do is to see if this is true. Are those objects that are, and we assume that astrophysical black holes couple with this power, is it consistent with having a horizon or not? By looking at our embedded cosmological black holes, what we see that the change in the Schwarzschild radius, that means change in mass, roughly in current epoch, not in the early epoch, but currently, if anything, it's negative and it's almost 0. So if this result is true, or which I'm not advertising in any shape or form, it's like quantum foundations. It's a sequence of if-then results. So if this is true, astrophysical black holes are horizonless objects. If you think that astrophysical black holes do have horizons, this is wrong. An interesting thing is try to see observational signatures. but I think I will skip this and go directly to the final slide. So black holes require as exotic matter as wormholes or exotic compact objects. Some of the popular models of regular black holes are wrong. A key feature is that spherical symmetry. You can either grow, but then you're a white hole, or you can shrink, and then it's a black hole. We get finite redshift. Apparent horizon is time-like membrane. We can get the formalism of membranes, exotic fluids. Collapse should happen in finite time, but we need to have a mechanism which turns all the positive energy density into negative one, and it's not clear that this is possible. Popular traversable wormholes are not static limits of allowed solutions, and static limits of allowed solutions are not traversable. And there might be linked to the observations. Now that the gang, so Robert Mann and Valentina Pacetti, my former postdoc, now faculty at RMIT in Melbourne. Sebastian Merck is now in Prague. Ioannis is going to be, well, mostly in Hangzhou, in Westlake, probably occasionally popping up here. Phil is now faculty at University of Waterloo. And yep, just remember, if you are nice to your supervisor, maybe you can get a trip to Sydney. Thank you.
Any questions?
So what's the key difference between the max PV
Finite time of formation. Finite time of formation according to a distant observer. This is because other requirements are totally non-controversial. Everybody says regular up to the apparent horizon, make some noises about compatibility with quantum energy inequalities. The real thing that forces you to have all those strange things in metric is finite time of formation according to distant observer. That's the key thing. And again, I'm not saying that real black holes are those. It is, if you assume this, it comes with all the baggage, and then it's potentially observational question if it's true or not. I don't know. We don't really know. That's why there is all this competitive sport. Find another model of ultra compact object. We've never seen the horizon. What we know that it's so far it's consistent, but again, popular like type to ultra compact objects, not physical or mathematical. To see the difference, you need to see the ring down up to tens or maybe hundreds of seconds. That means it's not even LIGO plus, but LIGO plus plus. So we're just not in the range to differentiate between those models. And what I'm doing, I'm just checking if we can throw in another class of models to distinguish between them. But this assumption is not innocent. It comes with a price. Finite time of formation leads to all of those things, from finite time of crossing to violation of the null energy condition to actually being more exotic than some of the designed exotic compact objects. Yes.
Finite time formation is not exactly the same as finite info.
No, it's
after the black holes form. For the distant observer, the new photon may still be infinite.
There is no reason why it to be finite, but it happens basically because apparent horizon for this black hole is time-like. So if you're moving sufficiently fast, you might cross in finite time. You might not cross as well. That's also a possibility. For massive point particles, you can get scenarios with, if you're sufficiently slow, you just float on Hawking radiation. So yeah, logically those are different concepts, and it wasn't assumed. It's what derived for some models. If you get a static limit, you might get again to the infinite crossing time. That's again, that's a possibility.
Another question is for these wormholes. Suppose there are distant wormholes existing, whatever kind, traverse ball or not. What can be the observational effects? Like if we try to observe,
Okay,
how
so
do we tell there is
observation again, according to Cardozo and the gang, having a wormhole might give you a different shape of the effective potential, and maybe also different boundary condition.
these can probably observe?
And that will show, and that may and they show up, and this may show up on in the quasi-normal mode spectrum. Because for example, some wormhole models, they give you the effective potential that you put into the Rayleigh equation looks like double well potential, and then and that will give you imprints on QNM spectrum. But that is really very much observer dependent.
Yes.
You're right. There are models which, if you take the limit that on outside it looks like Schwarzschild, the difference disappears. There are models, unfortunately, I think they're not very good because they assume singular layer of matter at the throat. It's a bit too much to me. Those models give you different spectrum. So the picture that I showed, that you have different lines on which quasi-normal modes lie, they correspond to the same extrinsic geometry up to the throat. So I'm not so it might be that many of those wormhole models are not really giving unless you assume too exotic stuff, they're not going to give you anything conceptually different. But so again, what I'm saying is that so long as you believe in semi-classical physics, you are not going to emerge, you're not going to create wormholes. It can be something that you inherited from the primordial universe.
Yeah, but suppose there were two wormholes nearby.
Oh, I don't know. That I see because everything which is not spherically symmetric is hard to calculate, so I just don't know. Okay.
Questions?
Does the possibility of traversing automatically
As far as I understand the literature, yes. Again, you need to have ability to manipulate the throat. So you have to be able to move it fast enough. But I believe that if you can create wormhole, you're advanced enough to manipulate it. So yeah, so mathematically, yes. And again, it's sort of uncomfortable to many idea. So what I liked in my arguments, to the extent that they're true, is that you don't look at the global properties. You again focus on local properties and get problem at that level. But yes, you are right. If you can build a wormhole, you can also build a time machine, at least of certain type.
More questions? I believe those students have taken advantage of your work. Questions at all?
I think not. I think not.
If you want to, no. See if there are questions coming from the tens.
Yeah, there are.
There is a question.
No.
No.
Yeah.
Oh,
No. Yeah. Okay.
If we want to build it's your time.
There are a couple of works which explicitly address it. I can basically, but yes. Answer is yes. But here I have to defer to Barak Shoshani and his group. Yes, that's so again, what I try to do is to avoid all those global questions and focus on minimal things that you can do, because, to discuss topology of the universe, you really need godlike abilities. I wanted to see if I can say something on modest scale. Now, again, honest story is not this. Honest story was after I learned that relate wormhole throws to marginal surfaces, I was sure that I have two classes of black hole solutions. So probably, and I dismissed one type of solutions because for black hole it doesn't work. So I said, maybe I can get dynamical, more restored wormholes from one class and dynamical Simpson-Visser from another class. So my attitude was opposite. Oh, I know how to generate dynamics. And then when I started to look at the dynamics, I've seen that these dynamics, yeah, I can generate these dynamics, but it leads to trouble. But it was still on local level, disregarding topological features on the large. Well, thank you. Thanks. Yeah.
Thank you.